Greetings, stargazers, and welcome to section 22 on the Big Bang. So what we're going to get into this section is we're going to talk about the cosmological principle. What does that mean? What does it help us understand the universe? And from there, we'll go and talk about Hubble constant and how that actually gives us an estimate for the age of the universe and even predicts the existence of the Big Bang. We'll talk about the evidence of the Big Bang, and we'll talk about things like elements that got produced during the Big Bang, what's called nucleosynthesis. So, bit of an abstract question for you, but let's start off by asking, where in the universe did the Big Bang occur? And obvious ones to think of, at the center of the galaxy, at the center of the universe, maybe it was the center of the Milky Way. If any of you enjoy a lot of science fiction shows, a common joke you'll hear in those things, especially comedies, are things like, well, it happened on the far side of the universe. And then there's this statement just about everywhere in the universe. So go ahead and pause, come with your answer, and come right back. So the vast majority of people, when I ask this question, they immediately eliminate the center of the Milky Way. Seems obvious, and I do agree. And this concept of the other side of the universe doesn't feel right either. And yes, you can eliminate that. So most people jump into, well, it's got to be the center of the universe, right? The universe was at this point, and that point blows up, and we're somewhere on the distant edge of that. But the reality is actually that the universe blew up everywhere. The universe started as this singularity, and that singularity is what's exploding into space-time. So another way to say this is that the Big Bang occurred everywhere. And I hope with an analogy that we'll build up in a couple of slides, this concept of everywhere happening can become a little bit clearer. So let's get into part one. We're going to talk about this expanding universe and what terms that we've developed to understand this. This picture you're looking at here is kind of a visual model of how the universe has changed in distribution of materials, how things look a little bit more uniform, a constant color, and has changed and gotten more and more various as time has progressed. So let's start off with a weird question. I'm going to ask you, where is the center of a stadium? Let's say if you ever go outside and you go to an event and you're in a stadium, how do you know what's the center of that stadium? Let's say you stood there. You stood at the exact center of that stadium. How can you be sure of that? Well, you could say, look, I'll hold up a measuring tape and I'll say, look, every part of the stadium is equally distant from me. I must be at the center. And I would agree. That's a good tool to say that's the center, right? You have equal distance to all things. Right. Now, we observe our surroundings to infer where we are, what's going on around us. And now we're going to start sprinkling in the stars and the galaxies and the cosmos and start to confound this question of where is the center? Instead of asking where's the center of, say, the stadium or the room, I'm going to ask where's the center of the universe? Where does that exist? So one term I have to build up for you is this idea of homogeneity. So this idea here is that I've got this blue solution and an orange solution. And if it's a homogeneous mixture, well, anywhere I scoop into that, I'll get equal parts blue and orange. It doesn't matter where I scoop, the thing is homogeneously mixed around. All right? So now let's go to the stars and galaxies. Our cosmological principle states that the universe is homogeneous and isotropic. And so here's my model example of the two astronauts who are on different parts of the universe. And what can they agree on? Well, they can agree on the distribution of material. Anywhere I look, I'll have basically equal chances of scooping up a star, scooping up a galaxy, or some dust. Right? The matter is pretty much uniform across the cosmos. And, even more so, isotropy. We're looking at how the universe is moving relative to these astronauts. So consider this astronaut. This astronaut, they look out into the cosmos. What do they see? Well, they see this galaxy going away. And they see this one going away. And so on and so on. So everywhere from this person's perspective, the galaxies are going away from them. Now let's switch up colors. What about this astronaut? What do they see? Well, same thing. They could wave at their friend, but their friend is receding away. An astronaut here would see the universe moving away from them. And that's what I mean by isotropy. Anywhere I look, I see the universe is moving in a similar fashion, and it doesn't matter where I exist in the universe, I'm going to see the same isotropic motion. Everything going out. So to repeat this is a homogeneous isotropic universe. It does not matter where I live in the universe. It does not matter which way I look. I'm going to see things looking the same. You might recall way back in the beginning of this series of lectures, we actually talked about the cosmological principle. And in that we said, hey, the laws of physics agree everywhere. Doesn't matter if I'm in the Milky Way or Alpha Centauri or way out in the distance, even further beyond. We will agree on the laws of physics. This is another way of saying that exact same principle. Homogeneous, similar distribution, and isotropic. Does not matter how I look, things will look the same. So, to help get these pictures in our brain, I'm going to look at model universes that don't fall into these categories. So here's an example of a universe where things are not homogeneous and they're not isotropic. So what do I mean? Well, if I took a scoop of universe here, I'd get a higher concentration, a denser amount of gas. But if I took a scoop over here, there would be less material. So this universe is not homogeneous. The matter is concentrated in that direction. It's also not isotropic. This observer will see more material going that direction than they do this one. But, more importantly, if I go to this observer, there's definitely a clear bias in how much materials are moving in what way. There's less material this way moving in a given direction. So this cannot be an isotropic universe. Let's try another one. All right. Here's an example of one where it is homogeneous, but it is not isotropic. Why is it homogeneous? Well, take a scoop here, take a scoop here, take a scoop here. All right. As I scoop around, there is a consistency in the distribution of material. A band, a gap, band, gap, band, gap. All right. So there's homogeneity in where the galaxies and dust is distributed. But it's not isotropic because if I look across a band, I'm going to see a greater distribution of stars. But if I look to another band, I'm going to have those gaps. So this is what I mean by it can't be isotropic. So to reiterate, I'm going to go back to the first one. This is a universe that we live in. Homogeneous. Matter is roughly equally distributed across the cosmic scales. And it does not matter where I look, we're going to agree on what the universe is doing. So, let's bring back Hubble's law. Right? Does not matter where I live, where I'm looking, the universe is getting bigger. And quite literally, what we mean is that the space between the galaxies is growing. And as we said before, it's accelerating due to that dark energy. So, Hubble established in what we now call the Hubble-Lumiere law. Lots of resources will shortcut and just call it the Hubble law. They established what's called the recessional velocity of the galaxies. They looked at all the galaxies and said, hey, the speed at which that galaxy is moving away, the recessional velocity, is equal to Hubble's constant, this h naught, times the distance to that galaxy. In essence, if I can measure the speed the galaxy is moving at, I can find how far away it is. And this was a critical tool that Hubble managed to establish. He used Cepheid variables across multiple galaxies to first establish this law, and we have since expanded it way beyond his work, and it still works incredibly well. Now, this Hubble's constant is a strange value, and I'm going to report it. I'm given two values. Our textbook uses the first one. Many resources use the second one. So Hubble's constant is reported as, today, 22 kilometers a second per million light years, or mega light year. Another common way it's phrased is still the kilometers per second, and this will be 70 kilometers per second per mega parsec. So if you do the conversions between light years and parsecs, you'll find these values are in agreement. And this is our Hubble constant. And that goes back into the Hubble's law of saying how far away a galaxy is, how fast is it moving. The further away, the faster it is going. So let's just do a quick, simple application of Hubble's law. Let's say, look, reminder, Hubble constant is that 22 kilometers a second per mega light year. And let's say I've detected a galaxy that is moving at 42 kilometers a second away from us. How far away is it? How far away is this if it's moving at 42 kilometers a second? So let's go through this step by step, right? I go back to Hubble's law and I say, here's the recessional velocity, Hubble's constant, and the distance. That's what we want to know. We want to know the distance of that galaxy. So divide by the Hubble's constant, get that to the left. Divide by h naught, and I'll have the distance is equal to the recessional velocity that we've measured, divide by the Hubble constant. And now let's work this out. Distance will be 42 kilometers per second, the speed the galaxy is moving at, 42 kilometers per second, divided by the Hubble constant, 22 kilometers per second per mega light year. All right, be careful, mindful of the units. Kilometers per second in the numerator, kilometers per second in the denominator, they cancel out. I'm left with 1 over a mega light year, which is equal to a mega light year in the numerator. Then I just do the ratio. 42 divided by 22 is about 1.9 mega light years. So this is keeping track of our units. Very important. We're going to come back to this, keeping track of what the units are. So let's come back to the issue that I've been trying to build up, the problem of trying to understand the expansion from us that live in it. So I'm going to use this rubber band analogy. Imagine that I have this effectively infinitely long rubber band, and I have paper clips going everywhere. Paperclip, 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 right? And what I'm going to do is just grab this rubber band and start stretching it out. So as time progresses, the rubber band gets longer, and the paper clips get further away. Keep going, and the ones that are further away will be moving faster away. So my little analogy here is encapsulating what we observe in the universe, that the further away an object is, the faster it is going away from us. Now for the crux of the problem, what's going on? If I ask anyone right now, what is the center of this rubber band problem? Everyone would say yellow. Everything's moving away from yellow. Yellow is the center of this problem. But what if you were an ant that lives on a paperclip? Let's say you're an ant on the red paperclip. What does the red ant see? Well, start stretching things out. Let's let time progress. Things get a little further away. Keep going. Things keep getting further away. And so the red ant sits on his paperclip and goes, everyone's going away from me. I'm the center of the universe. Everyone is moving away from me. Well, now, let's say you're an ant that lives on the green paperclip. And what does the green ant see? Repeat. You live on this paperclip, you look at the cosmos, and it's moving away from you. It's getting further away. and getting further and further away. So the green ant will say, hold on a second, the universe is centered on me. Everything's moving away from me equally. And so the crux of the problem is that all observers, or in this picture, all ants, have equal valid claims to being the center of the universe. Because as far as they can tell, everything's moving away from them at an equal rate. So this becomes this weird conundrum of how do you define the center of the universe if there is no stick for me to define the edge of the universe? Everyone is moving equally away from me at an equal rate. All their speeds proportional to how far away they are. So all this is invocative of that Hubble's law again, right? Increase the distance, increase the recessional velocity. Interesting note here, when Hubble resolved the Great Debate, this is the only range of data that he had access to. He was looking at C5 variables inside nearby galaxies. But in the near century since Hubble, we've managed to expand his work and continue replicating the Hubble's constant as the slope of this curve of velocity versus distance. So now we're going to do this deep analysis of this Hubble constant. What is it? And I'm going to keep using the 22 kilometers a second per megalight year. And if we were to simplify the units alone, ignore the numbers, just say what are the units, what should we get? What physically does Hubble's constant measure? I'm not going to give it to you on this slide. Obvious answers, velocity, distance, time, or inverse time. These are all the physical parameters. Let's look at it with analysis in our heads. Here's the Hubble law of the recessional velocity constant times the distance. Well, remember, what is a velocity? I traveled 50 miles in an hour. I was driving at 50 miles per hour. So velocity is a distance per time. Well, a velocity and a distance, Hubble's constant itself better be 1 over time, or inverse time. Let's check it in detail to confirm. All right. H naught, 22 kilometers seconds inverse seconds per megalight year. Write this out in a bit more explicit form. That is a kilometer per second, 1 over a megalight year. That should be a plus now. Right. 1 over megalight year. So kilometers. Is that a distance or a time measurement? Distance. So if I look at just the units, I only care about the units now, not the numbers. We'll get to the numbers on the next slide. If I look at just the units, a kilometer is a measure of distance. Seconds is a measure of time. And a megalight year, sure it's big, but it is just a measure of distance. So the Hubble constant will cancel out the distances, and it does physically mean 1 over time. Well, the following question is, if H naught is 1 over time, let's calculate what 1 over H naught is. Figure out what the time, or what we'll call Hubble time is. 1 over H naught. So now we do need to be careful. We need to keep track of our numbers and our units. So our Hubble time, 1 over H naught. That's going to be 1 divided by 22 seconds, megalight years per kilometer. Now let's go through this step by step. Megalight years is a big number. I want to get these into units that I can comprehend. So I pull out the mega as a 10 to the 6. And that's where this 10 to the 6 came from. I dropped the mega part and just wrote it as a power of 10. Next step, I have light years per kilometers. Both of those are distance measurements. I want them to be the same unit so I can cancel them. So now what I'll do is multiply by the number of kilometers in 1 light year. And there are 9.461 times 10 to the 12 kilometers in a light year. All right. This 9.461, just going to slide it over here. The 10 to the 12th, what happens to that? There is this 10 to the 6th term. So I've got 10 to the 6th times 10 to the 12th. Well, that is now just the addition of exponents. 10 to the 6 plus 12. 6 plus 12 you should be able to do in your head. And that's the 18th. So that's where this 10 to the 18th has come from. It was a combination of 10 to the 12th multiplying 10 to the 6th. Now let's cancel out units, let's simplify. Light years go away, kilometers go away. And now I'm left with 0.43 times 10 to the 18th seconds. The 0.43 came from this ratio. So, grand conclusion. What is 10 to the 18th seconds? No idea. I don't know what 10 to the 18th seconds is. It's just big number. So what I'm going to do is convert this from seconds to years, because years is the biggest time unit that my brain is content with comprehending. So let's convert this, right? There is 1 minute and 60 seconds. So I've canceled the second units. Need to go bigger. Well, how many minutes are in an hour? There is 1 hour and 60 minutes. The minutes have been canceled. Okay, I keep going. There is 1 day in 24 hours. Cancel the hours. I'm now in the unit of days. How many days are in a year? There is 1 year per 365.25 days. So I'm left with the unit of year. Multiply this together, do it all out, and what I'll end up finding is that the Hubble time is 13.6 billion years. The age of the universe. Hubble was just looking at trying to figure out how big the universe is, how far away things are, how quickly they're moving. And he inadvertently invented a new tool for measuring the age of the universe.